Everyone to Introduction to Astronomy. Are there any relatively new members like here within the last 3 or 4 months or so? Yes, hello. Oh yes, a few of us. Oh good, welcome guys. So the talks for Introduction to Astronomy, we try and pitch them at a wide sort of pitch because there's quite a variety of people here, so there'll be something for everyone. We usually like to pick a topic, and within that topic there'll be 3 or 4 principles, really key principles, ideas and concept of astronomy, which I'll purposely for you guys pull out and expand on and put them back in their place and carry on. So it's the talks for everyone. So let's get going. Get this moving along. Our sun is a mature, middle-aged main sequence star. By main sequence, by definition, that means it's in a relatively stable state where it'll spend 90% of its life, fusing hydrogen at its core into helium via nuclear fusion, which generates the energy that gives us heat and light from it. So that's by definition. That's what our sun is. But have you ever wondered, how did our star first form? Where did it first form? How did it develop into the star it is today? And this field of astronomy has always sort of been, up to recent years, has been a difficult field because the regions where stars form, as you can see here, this is a Hubble Space Telescope image of the pillars of creation within the Eagle Nebula, M16, in the sky. And you can see that these big pillars where there's star formation going on, they're all thick, dense, opaque cloud. And the reason you're seeing that cloud is because it's a bit of light being reflected off it, and also indirectly the silhouette, because it's just blocking all the light from the new stars forming. So it's been a very difficult area of astronomy because you can't get into it. But with recent years, in particular the James Webb Space Telescope, you're able to start cutting through. Infrared light can cut through the dust, and suddenly you start seeing, oh, look at all these multiple stars here you couldn't see before that are all in there, that you can now see and start to study infant stars. And that's why tonight's talk is titled Revealing the Youngest Stars in the Galaxy, where tonight you will learn where stars form, how stars form, such that you can look at images like this, you'll be able to identify infant stars in various stages of development, and also various structures that you get in combination with these stars as they're forming. More importantly, tomorrow morning you'll be able to wake up, find someone and tell them, hey, do you know how our sun formed? You've got to tell someone tomorrow how our sun formed, where it formed and how it developed. So I've split it up into these chapters, regions of star formation, because it makes sense that if we're going to be studying them, we want to be able to know where to look and where to find them. The objects of star formation, that's going to be the main thrust of the talk. What sort of objects make up these infant stars? Then I've got a nice, there's a lot of information to take on board with objects, so I've then got a nice flow diagram which we'll work through, just summing it all up. Then we'll go down and have a look at some images of star formation and how new telescopes are helping. And then we'll finally tidy up with a brief conclusion of what you've learned. So, regions of star formation. Where do stars form? How do you know when you're looking at one of these regions? So I've just put 4 key things that you'll find in regions of star formation: giant molecular clouds, dark nebula, H2 regions, and Bok globules. And probably a lot of you already heard of these terms. Some of you will say, oh, I've heard of these terms, but I'm not sure exactly what they are. So let's move on and let's talk about giant molecular clouds. The bottom line, these are massive clouds, and this is how star formation all starts. They are giant, they are large, they are many light years across. Now, a light year is the distance that light travels in a year, which is 10 million kilometres. That's 1 light year. And these things can be hundreds, up to 1,000 or so light years across. So I don't need to say anything further. They're large, they're giant. You can see how they've got their name, giant molecular clouds. They are very dense. To give you an idea of how dense they are, the interstellar space in our local neighbourhood, around between our star, the Sun, and nearby stars, you get about 1 particle per cubic centimetre. 1 particle per cubic centimetre. That's the general density of space outside our solar system in our neighbourhood. In these clouds, you can get anywhere between 100 and 1,000 particles per cubic centimetre. So they're 100 up to 1,000 times more dense than the interstellar space in our local neighbourhood. So they're very dense, they're very cold, and they've got to be cold because the giant molecular part of the word up there, molecular means that molecules, that little elements and atoms have come together to form molecules. And in normal space temperature, there's a bit of movement going on, and there's too much movement, it's too warm for them, where atoms can't join up, they just keep moving apart from one another. So how cold? About 10 to 20 degrees Kelvin. You might say, whoa, what's that in normal temperatures? That's about sort of minus 260 odd degrees Celsius. Pretty cold. Though my daughter says try a student flat in Dunedin in the wintertime, you might get a better idea. So it's pretty cold. So that's what characterises these giant molecular clouds, and this is where all star formation starts. Just to show you further how much these extend, these molecular clouds, is that you probably recognise this constellation here. It's upside down as far as we're concerned, but obviously this is from the northern hemisphere. This is the constellation Orion. See Orion's belt? There's Orion's sword hanging down, but for us that is the handle of the sword. There's Rigel there, and there's Betelgeuse up there. So this point of light here that we just see as a sort of a bright star, if you will, that's the Great Orion Nebula, and that's a star formation region in the sky, but to us it just looks like a spot. Now that image there is taken in visual wavelengths. Now let's have a look at that same region of sky in infrared. Woohoo! Dust emits infrared light, and suddenly you look at that same patch of sky, and that gives you a much better idea of the size of the Orion giant molecular cloud, which is typical of a lot of giant molecular clouds out there. So these clouds are large. So how does it all get started there? Well, these clouds are just sort of in a state of equilibrium. They're just hovering around, they're reasonably stable. And it would be reasonable for you to think, well, you've got gravity out there, and you've got all these particles that you've just told us are fairly dense. Why aren't the clouds just starting to collapse in? They're actually held up against gravity by 2 factors. One is what they call the gas pressure, the heat pressure. In other words, the molecules are moving around a little bit, and collectively that's enough just to push against the inward gravity with the assistance of what we call pressure from embedded magnetic fields. Magnetic fields are intricately interwoven throughout of all the universe, all through space. You've just got magnetic fields through there. You've got charged particles. Charged particles give rise to magnetic fields, and magnetic fields tell the charged particles how to behave. And these are fairly dense areas, so there's quite a few magnetic fields embedded and interwoven throughout these clouds. And that, of course, influences the behaving, gives a bit of pressure to charged particles in the gas and dust in these clouds, and that acts with the gas pressure just to offset that inward force of gravity, so it keeps them stable. And then something will come along to trigger these clouds to start collapsing. And there's a few things. It might be a collision between 2 clouds. It might be a nearby supernova explosion going boof, and the shock waves just head into a cloud. Passing through a spiral arm of a galaxy. So spiral galaxies have these big pressure density waves just sweeping through them, and they go just slightly faster than the stars are moving around the galaxy center. So you could be in a cloud, and a pressure cloud, density cloud is coming up behind you and starts compressing this molecular cloud. That will start the process going, will break the cycle and interrupt that whole nice little balance going on. And of course the other one, when you get galaxy mergers, 2 galaxies come together, of course you get cloud mergers and collisions, and that upsets things as well. What happens from there is the cloud starts collapsing in on itself, but it starts breaking up. Nature does not like large, unstable things. It likes to break up and start fragmenting. But the fragmenting also starts to cascade. As big starts going to big fragments start breaking into smaller fragments, and it just goes down and down and down. And each of those fragments, or what they call them is clumps, once they're finally fragmented down to the before it forms a star, each of those fragments, known as a clumps, collapses down to a dense core, and that's known as a protostar. And we're going to come back and visit that in a minute. So that's in the context of giant molecular clouds and star-forming regions, and the relevance of them for star formation. That's the very, very beginning of stars getting underway. So that's giant molecular clouds. How about dark nebula? What are they all about? And the bottom line is they are just molecular clouds that are relatively close to us and really ultra dense, whereby they block the sunlight, or rather the sunlight, the light coming from distant stars, and these things are relatively close, and you see big dark patches in the sky like that. These naturally are very important areas of star formation because they're very cold, very, very dense, and of course they're relatively close to us, hence blotting out the starlight from behind, so a bit easier to study. The guy, an American astronomer called Barnard, he was the first one to recognise them and started cataloguing them all, and so they're also known as Barnard objects. Now, you might think to yourself, oh, that looks interesting. I wonder if there's any of those in our neighbourhood that we can see in our night sky. Absolutely. So here's the Southern Cross here, here's your pointers, and in this dark patch right over here, you'll see the coal sack. You need a dark, moonless night to see it, but you look between the pointers and the Southern Cross, next time you get a real pitch black, dark night, and you'll see, if you look close enough, let your eyes adjust, you'll see a big black patch. That's known as the coal sack, for obvious reasons. It looks like a sack of coal. So we do have one of those nearby that we can see. Okay, how about H2 regions? So that you probably see in pictures and stuff, you see all these pink areas. Most people recognise that. That's M42, or the Great Orion Nebula. That picture that I showed before of Orion's belt, or the handle, the bright spot and bang in the middle of the handle of the pot, that was the bright star that you're looking at. It's a region of star formation within that bigger cloud. And what's going on here is that when you get a region of new stars forming in a cloud, big stars always start developing first. Why? The main driver in astronomy for things on decent-sized, large scales is gravity. And of course, what drives gravity? Mass. So the bigger you've got of something, like a bigger star, something of bigger mass, is going to have a bigger gravity, bigger inward forces, which means it's going to collapse down a lot sooner and get going into a star. So the massive stars are always the first to arrive when you're starting to get a cluster of stars starting to form. And these big stars emit really high energy ultraviolet light. And that ultraviolet light, what they call, ionizes hydrogen atoms in the molecular clouds. As you remember, a hydrogen atom is just a proton essentially for its nucleus, and that's positively charged, negatively charged electron. Along comes a high energy ultraviolet light, photon, energizes the electron and bumps it off. And then as soon as that photon's gone, it's been absorbed, the electron naturally wants to come back close to its positive proton again, so it falls back again, and it emits a light called Balmer lines. And they are in visual wavelengths, that pinkish, reddish hue that you get, and that's what's going on. Just a little side note, those massive stars, not only are they the first that get up and running amongst these molecular clouds, they are the first to go quickly burn through their lives and explode and go supernova, such that by the time your average sort of stars and your smaller stars are starting to get born and get going in these molecular clouds, these big massive stars here are been and gone. They've long left the scene. Your big stars that you're looking here, you're starting to see these guys around in here. That's where your big stars are. And there's all this sort of hydrogen atoms throughout here because it's still part of the gas and cloud, and they're all being ionized or energized, and then they fluoresce. Essentially, it's a process of fluorescence. Now, you'll see this type of diagram a lot, this a photograph, an image like this. This is a spiral galaxy. This is what our Milky Way would look like if you're from a reasonable distance. But you can see the spirals here. And what do you notice about these spirals? All these big red spots. And these are all H2 regions. And that's where, another point is that's where star formation occurs. It occurs in the spiral arms of spiral galaxies. And you see these pictures, and often the first thing people say, what are all those red spots doing in there? They are H2 regions. They are areas where new big giant stars are up and running, blazing out ultraviolet light and energizing or ionizing hydrogen atoms. And that's what you're looking at. Okay, how about Bok globules? So essentially what Bok globules are, they're dark nebula, but they're really particularly relatively small ones and quite isolated. And they've been sculptured into all sorts of shapes, pretty much like clouds, in the sky. Winds are shaping them. It's the same thing here. There's a lot of stellar winds of massive stars going on, and you get little particularly dense, small, isolated areas that's sculptured like that. That's called the Caterpillar Nebula. It's quite cool, isn't it? Someone said that the head looks a bit like a reindeer, which I agree. So I thought I might make it a Rudolph. Look, there you go. There's Rudolph for you, the red spot. Okay, so that's, and they're all sort of shaped, once again, like clouds. They get nicknames from what they're called and so on, because it's like, you look up in the clouds and you see cloud getting sculptured by wind and stuff. You can see all sorts of shapes. They're within H2 regions, so they're nearby these massive stars, and it's the big winds, stellar winds from these massive stars that are shaping them. They're usually up to about 50 solar masses. Another little concept here. The unit, a lot of units in astronomy, and mass is one of them, that's how do you start using units? They call them solar units, and it's related to our sun. And for example, one solar mass is the mass of our sun, which is roughly about 2 times 10 to the 30 kilograms. But rather remember that, just remember it's one solar mass. So for example, if there's 2 to 50 solar masses, there's this 2 to 50 times the mass of our sun in that. And often you'll see it here with a big capital M with a circle and a little dot in the middle of that circle, and you'll see it as a subscript. And that when you see that subscript, that means solar. It's meant to be the sun. So if you see a big capital M with a little circle and a dot in there, that means a solar mass. Same if you see a big L for luminosity or brightness. You see a little circle with a dot in the middle. That means it's one, or how many of it is, solar luminosities or brightness of the sun. And you'll see the same with sizes of other stars. They'll put a big capital R for radius with a little dot. It might say 10 big R with a little dot and circle, and that's referring to, means 10 times the size of our sun. So that's just another little thing that I've pulled out there. These usually about a light year or so across. This one here is about a light year across. And they typically, because they're fairly dense and isolated, they give rise to multiple star systems. Most stars anyway comes in 2s and 3s and 4s. Our sun on its own is a bit of an exception. Okay, so that's regions of star formation. Those are sort of, think, I wonder where the stars could be forming, where we could have come from. We would have come from a region like that. So there's some features there you can look out for. If you see those features, you know you're looking at a region of star formation. So how about these objects? This is an interesting little picture. This is a region of star formation here. And all these little pink orbs or blobs here through the middle, all of those are infant stars that you wouldn't normally see. This image was taken by the WISE, which is the Wide Field Infrared Surveyor Explorer telescope in space. It took its infrared image of the Ophiuchus cloud complex, so you would normally not see these in visible wavelengths. Since that got decommissioned from this job and then worked from 2013 to 2017, I think it is, it was actually then working on identifying, characterising near-Earth objects, like asteroids, potential rogue asteroids and the likes. So that's another use of infrared astronomy. So all of those little pink orbs there are all infant stars, future suns. So let's have a closer look. Now, these infant stars are then divided into 2 types, protostars and pre-main sequence stars. It's a real key thing to take home. There's various structures that formed with the whole process of stars forming and developing. It's just easier to introduce them because you first see them in the protostar phase, so I'll be talking about them there as well. Now this shows you that star formation is divided into various stages and classes to make things easy. And you can see here starting off with your clump, moving on to protostars and your pre-main sequence stars, and then eventually ending up here with your main sequence star, which is our sun, which is burning hydrogen to helium and that at its core. And that is the key thing. That defines a main sequence star. You know you've got a fully fledged star on your hands when you're burning hydrogen into helium. And that's what it's all about, getting a star hot enough to burn hydrogen to helium in its core. Now, how do you break up these stages and classes? It's based on the big dust cloud that we talked about, you know, when these fragments all develop into clumps. So it's all about the big gas cloud and so on, how thick and how large it is. Now, the other thing is you notice that the size across here is going lower and lower and lower as you go down. An AU, another little astronomy principle, an AU stands for astronomical unit, and that is the distance from the sun to the Earth, which is 150 million kilometres. Once again, why bother dealing with units of 150 million kilometres? Just deal with one astronomical unit. So to give you an idea, in our solar system, Neptune, the furthest planet out, is about 30 AU, 30 astronomical units out, just to put things in perspective. The Kuiper belt, a big donut-shaped sort of belt of rocky objects that give rise to short-term comets, they've ranged between about 30 and 50 astronomical units. So I just put that to give you an idea, a perspective of our solar system. But these big clumps that are going to develop into individual stars, they have a diameter of 30,000 astronomical units, which means that they're 60,000 across. Have you any got idea how far 60,000 astronomical units are? Get your calculator out. That is almost a light year across. Remember, a light year, 10 million kilometres across some of these big dust clouds or clumps. They're called clumps at this stage because that's a unit of dust cloud that's collapsing onto itself to form a star. So that's the size, and then you'll notice here slowly as you define each class and stage, you go down and down and down, and they get smaller and smaller, and then eventually get to the pre-main sequence. And here's a solar system that's developed with planets and 50 astronomical unit size diameter, and that's more comparable with our solar system. So you're looking at the dust cloud, you're looking at structures, and we're going to talk more about it, but you can see here from this diagram here that, you know, there's structures developing at each class and stage here. You've got different structures going on. Peak emission, when you start looking at them, the peak wavelength at which you see these objects, they change as well. For example, class O, its peak wavelength is what they call sub-millimetre wavelengths, which for the technically minded is about 500 microns up to about 1 millimetre. Class 1, you start looking into the far infrared, which is about 40 microns up to about 400 microns. Class 2, you're now getting down to the near infrared wavelengths, which is up to about 5 micron wavelengths. And then you get into class 3 and even some of the class 2s as well. You're well and truly getting into, you can see all these invisible wavelengths now. And probably one of the take-home messages to start to you right now is that what defines a protostar from a pre-main sequence star is that the protostars are still enshrouded in thick dust. You can't see them except in infrared. And your pre-main sequence stars, you're starting to see them in visible light because all the dust and that is clearing. For some reason on this slide it's not so obvious, but you can see here the dust is getting less and less each time. That it's normally a grey colour, but obviously for whatever reason it's white here. But you can see that white fuzzy haze has just got less and less each time you go. Now people often ask, what's this whole diagram about a class 0? What's that about? And it's typical in astronomy. Historically they start classifying things and they realise, oh, I don't think we really understood that, but let's leave things as they are. We'll create another one. So there was a class 1, 2, 3, and that's when they went, oops, we'll have a class 0. So that's how you got that. So yeah, there's stages, the two big stages, protostars, pre-main sequence stars, and they're broken into class 1, 2, 0, 1, 2, rather 3. So let's look at these prestellar cores. So we touched on these when we talked about how giant molecular clouds start collapsing down. So how to build a protostar? Well, initially, with gravity, you're getting all this collapse of all this dust and cloud that's coming down towards the core. And in the initial stages, the density is not too great in the core, such that it is still transparent to photons, to light, radiation, heat. So as it's condensing down, any heat and light that's been generated can escape from that core. So in other words, there's no pressure to stop it, so the collapse just keeps going down and down and down, as long as that's transparent, keeps collapsing. Then it slowly gets to a critical level where the density rises, whereby it becomes opaque to photons, or radiation, light, heat radiation, whereby it gets trapped, so the light and the heat can't get out, so it builds up in there, and it starts resisting the infill. And you reach a state of what they call hydrostatic equilibrium. And that's just a fancy word in astronomy to say, hey, the outward forces are balancing the inward force of gravity, and you've got something that's a nice stable state of size. And that's called hydrostatic equilibrium. And by definition, you now have a protostar core. You're in that class 0 now when you get to that stage. Class 0, you've still got a lot of cloud and gas going on here, but something's going on here. You can just start to see the beginnings of a little bit of a disk structure going on here, like a big donut shape going on, so it's no longer sort of all a big spherical collapse going on. Why? Because that protostar is putting a halt on it. You're getting these little jets starting to form. So I think before anything else, we'll move on to the next class, because I don't want to spoil it for you. But you might say to yourself, how long does all this take? Class 0, and on your handout there's some times there. They are more applicable to a star of 2 solar masses. So I've adjusted them, did it this afternoon, I adjusted them on the slides for more comparable to 1 solar mass else, because that's at the end of the day what you're going to be doing. You're going to be telling all your friends tomorrow how the sun formed. So when your friends say to you, well, how long does it take to get to this stage? Roughly the sun took about 30,000 years to get to this stage, to complete class 0 phase. Then you get to class 1. Notice the size. You've come down from a light year, or 30,000 radius, down to 10,000. You're down to 300, so it's coming down considerably, 1/100th the size of that clump now. And you're starting to get this disk forming here, and this is a nice picture of what the disk looks like, more of a 3D type of picture. And these jets coming out. You might say, what's that all about? And it's just a thing of nature. You get a spinning, I didn't mention here, but these clouds, as not only are they collapsing down, they're also spinning round, and they're getting faster and faster. And you may or may not have heard of the concept of conservation of angular momentum. And it just means if something's spinning around, as it gets smaller and shrinks down, it spins faster and faster. And just think of your ice skating. Your lady on the ice skating, you know, she's got her arms out at full length. She's skating around, yay, fast. And she brings her arms in, and then she starts shooting around really, really quickly. So if something's spinning and shrinking in size, it starts spinning faster and faster. Angular momentum just refers, it's a function of how fast something is spinning, with its sort of size outwards, its radius that it's going as well. It's a combination between the two. So shrink the radius and your spin rate goes up. So it's a thing of nature whereby if you've got a cloud or anything that's spinning around and collapsing on itself, particles start colliding. And you start, the particles, as they hit and strike one another, impart energy to one another, they start developing, all of them start developing into the average sort of velocities and motions of all the particles combined. And that happens to be in a nice equatorial plane. So you always get a disk form. And the same principle, someone said to me today, is it the same thing that occurs around a black hole? Absolutely, black hole. You've got all this material spinning down into, into a core of the black hole. You get what we call an accretion disk, and this is called an accretion disk. The word accretion in astronomy just means to come inwards and under gravity and go into fall onto a star or black hole or something like that. That's the word accretion, fall onto something. So you start getting this disk form, and the material, because the protostar says, I can't take any more on here, thank you very much. So most of the material starts falling now directly, starts raining down onto the disk here. And then the material starts going inwards, because it's all spinning around, and with gravity and friction, it starts slowing down, and it starts moving round and round and round, and then eventually a lot of the material will fall onto the protostar. Pretty much like when you pull the plug in your sink. The water goes, spirals down, and eventually goes down through the middle. Now, how about these jets? What's going on here? Remember I said there was a lot of magnetic field lines interwoven throughout all the space, all these clouds and stuff, because there's charged particles. Particles are heating up in here, so they're getting more charged, so they're pulling apart. The more charged, you're getting stronger magnetic field lines. The magnetic field lines are going inwards as well, and they're getting twisted and distorted as they go in. And then they get to about here, the inward part of the disk, and the magnetic fields get twisted and distorted and head out along a path of least resistance, which is along the rotational axis of this rotating protostar. What follows magnetic field lines? Charged particles. Yeehaw! Here's some magnetic field lines. Let's charge. Let's go, guys. So you get these big jets going out here of all these charged particles. And giving you an idea of what are these jets like, the material shooting out of these jets is traveling at hundreds up to thousands, usually 500-600 kilometers per second. Check that out, 500-600 kilometers per second. That's how fast, how powerful these jets are. They will extend out to about 3 light years. Remember, 1 light year was 10 million kilometers? Well, each of these jets going that way can be up to 3 light years and going 3 light years that way. So imagine 30 million kilometers each way at 600 kilometers per 600 kilometers per second. So that's sort of, it's a pretty sort of feisty sort of place to be hanging out. So I've put here, so essentially where I've gone on about the inward spiral of material and magnetic fields, you get these bipolar jets. Now, the bipolar jets serve a very, very useful function. What do you know about something spinning around, like the protostar? Something spinning around, Neville? No, I'll just keep... Yeah, similar. Yeah, so that's right. Yeah, pulsar. So if you've got something spinning around, not only is it not going to want to take material on, what happens when you're something spinning around really quickly? Things start flying apart, don't they? The centrifugal forces. That protostar at this stage is about 1% of its final mass that it's going to be when it's an eventual star. So you wouldn't have much of a universe or a galaxy like that. So the protostar is spinning really, really quickly. But these jets serve a function. They bleed out that angular momentum, in other words, drain off the spin velocity, and they slow the protostar down, which enables the protostar to accrete more material onto it. So that's a very, very useful function. If it wasn't for those jets, we wouldn't have these most stars. This, for the sun to get to the end of this stage, was about 300,000 years. So the other thing mentioned here too is that as that cores, as it accretes more and more material onto it, gravity's getting a grip on it, and because it's getting more mass this time, so it does keep contracting down, and it gets hotter and hotter in that core until it reaches about 1 million degrees. And that's a very important figure, because at that figure, deuterium fusion kicks in. Deuterium is just an isotope of hydrogen. Let me explain. Hydrogen, the nucleus is 1 proton with an electron. And the word isotope just means it's a proton that defines the properties of an atom, the positive charge in it. But you can throw in some neutral subatomic particles called neutrons in there, which increases the weight of the atom, but it doesn't alter its chemical properties. So it's called, just a fancy word, it's called isotope. So the isotope of hydrogen, a normal hydrogen's got 1 proton, but you can quite happily bring in a neutron next to it, and it's called deuterium. And it's just what they call an isotope of hydrogen. So that deuterium is in the mix, and that can start fusing together at about 1 million degrees Kelvin. Takes about 10 million as our target to reach main sequence stage. About 10 million degrees to start fusing hydrogen, just a proton on its own. So you're a tenth of the way there, but deuterium fusion kicks in, and that has 2 important functions. One is that stabilizes the temperature of the protostar. So it's like boiling water. You boil water, the temperature rises to 100 degrees Celsius, and then while the water's boiling, it levels off. It doesn't just keep going up. And it's the same principle here. You start burning deuterium, and the temperature starts leveling off. So it puts the brakes on the rise of the temperature because you're burning deuterium, which means that you can accrete more material. Because if you get a hotter object, that's going to be flying stuff off as well, which is going to impede build-up of mass. So you've got a you're starting to get a control on the temperature of the surface of the protostar, and that once again helps to create more accretion of mass onto it, helps it to grow in size. But it creates some more temperature to drive what they call convection. That's the transfer of heat from the core of the star and getting it out to the surface. There's two ways stars can do it. One is convection, and that's where you get little packets, little units of material, in this case gas, heats up, and it starts to expand, so it gets low density, that little packet, so it starts rising, gets to the surface, gets rid of its heat, so it cools down, so it gets more dense, contracts, and of course more dense, so it falls back down again, and it's a cycle. What everyday thing does that? When you boil up the electric jug. So next time you're making yourself a cup of coffee, you go, oh look, I'm looking at convection. So that's one way, and the other one is radiation, is where you get straight light, radiation of light, photons, particles of light, just zipping straight out directly. Your big bar heater sitting on your wall blasting out light, that's radiation. Your lights, those lights are radiating light, so they just come out unimpeded. So convection is a very efficient way of losing heat, getting rid of heat. So it starts driving convection going throughout the whole protostar, and that's another factor to help get rid of heat, stop the protostar from overheating, and encourage more mass accretion. This is a nice little diagram here showing, sort of giving you a more visual of this. So here's your protostar in the middle there. Look at these. This is the big disk around here. You can call that, you get that disk named all sorts of things. You might get it called one day a circumstellar disk, a protostar disk, protoplanetary disk, an accretion disk. It's all one and the same. Often it refers to what stage you're along. This stage it's probably more appropriate to call it an accretion disk because its prime purpose is to accrete mass onto it and then put it onto the protostar. But there's your jets coming out there as well. There. So that's just a nice little diagram to help visualize that in your mind. Here's some lovely James Webb Space Telescope images in infrared. So here you have, and this is in the Taurus region. So sitting right in the middle there, that's sort of those sort of darker regions here. See, you've got this bit of glow here and a glow here and a dark little strip in the middle. Looks like a hamburger, doesn't it? So what looks like the beef patty and your hamburger in the middle there, that is your accretion disk of a protostar in the middle. That's your disk. You can't see the protostar. It's still enshrouded in thick cloud and a lot going on there, but that's amongst that. Like right in the very, very center there is your disk. I think I've labelled some of these here. So there's your protoplanetary disk or your accretion disk. These areas here is the protostars getting rid of heat and light and so on. So it's lighting up or illuminating all the gas and dust around it. Your jets are in there a lot firing out as well. And what your jets are doing, so you've got interstellar space all around here. And don't forget, you've just had a massive cloud that's still a bit of dense material that's coming in here, accreting onto the disk. And suddenly you've got these jets of material heading out at 600 kilometers per second for 3 light years. It's ramming into the interstellar material as it's shooting out, creating bow shocks, like a boat going through the water, creating bow shocks. And those bow shocks are very, very forceful and energetic, and they give rise to pockets of bow shocks or pockets of energized or ionized material. And that's what you're looking at here. These big patches here, these are sort of like shock waves of energized material. And when you see those sort of like mini emission nebulas, they are called Herbig-Haro objects. Just the name. There's a couple of astronomers. Herbig and Haro was involved in all this research. And it's the hot ionized gas coming out in jets and colliding with all the material and the gas and dust. And you get these patches of nebula. And they call them HH. If you ever see something, look at object HH in an image from the James Webb or the Hubble, with its near-infrared images, you know they're referring to a Herbig-Haro object. So you immediately know, I'm looking at a region of star formation. And that's what you're looking at with these objects here. It's jets of hot material shooting out at hundreds of kilometers per second, ramming into the material. Here's a nice little diagram of what's going on. Here's your accretion disk and your protostar. Look at these jets, and is a bow shock there. And you get multiple bow shocks with the same jets quite happily. Here's another one here in the Orion cloud. There's a class 1 protostar in the middle. These jets here are 2.6 light years in each direction. And look at these little clumps. Because once again, nature's not perfect, and it's just not a steady stream necessarily of material. Nothing's perfect. So you get little clumps. You get a dump of material, and some falls onto the protostar and some shoots out in the jets. So often the jets will stop and start or splutter and so on, or you get thicker patches of the jets, and that's what helps to create these bow shocks. And that's what you're seeing there. Pretty impressive. This is a lovely picture. This is the Pelican Nebula, which is part of the Carina Nebula, and you see this lovely big pillar of thick, dense, opaque gas here. Dust rather, that we saw with the pillars of creation. You can't see, and you know there's a protostar in the middle there, because look what's hanging out at the end of it, these two jets shooting off in either direction. And you notice these big, I'll put the spotlight on it there, so you can see the big jets shooting out here, and look, there's emissions out to the edges here, and you can't see it here, but there's tiny little ones in there as well. So that, once again, they're jets with Herbig-Haro objects. Love that picture, gorgeous. Okay, so here's an image you're probably familiar with, one of the images I put up at the start, and this is called the Cosmic Cliffs, and it's from the James Webb Space Telescope in near infrared wavelengths. And what I've circled in there, you'll see these little flicks of gold that NASA's kindly coated them in gold and yellow and so on, where I've highlighted and red circles around them. They are jets and Herbig-Haro objects when you look at them. All these little points of stars all throughout here, these little tiny little stars, there's just hundreds of them through there. They are all protostars and pre-main sequence stars. Essentially, they are infant stars at various stages, and you see these big streaks like that, and they are jets and Herbig-Haro objects when you see them. So that's a lovely patch of the Carina Nebula there, an area of star formation. You can start seeing all the dust and all the details in the dust. As I showed at that one before in M16, the Pillars of Creation, in visual wavelength, all you could see was just this silhouette of the dust, really. It was blocking light behind it. But suddenly you're actually seeing the dust itself. And that, once again, you start analysing that dust, looking at its patterns, spectroscopy, work out what atoms are going on, elements and molecules in there. You're getting a better grip of star formation process. So you can actually see the dust directly, not indirectly. So you can see, James Webb is just going to open up a whole field of astronomy, how stars form. So that's protostars. How about pre-main sequence stars? And as I alluded to before, protostars are still enshrouded in thick dust. Once they've cleared it, and you can start to see them in much better in visual wavelengths, they become, by definition, pre-main sequence stars. They're divided into two, T Tauri stars and Herbig stars. And Herbig stars are split up to A and B. I'll show you in a minute on a diagram what that's referring to. That's the A and B spectral classes, and the little E subscript stands for emission, because you look at their spectra and these spectral lines, but we'll come to that shortly. So a protostar has blown away its envelope of gas and dust, and by definition now it's a pre-main sequence star. It is now optically visible, and here's the excitement. Of course, I know you're just building up to this. My God, you think it's visible, invisible wavelengths. What does that mean? It can be charted on the Hertzsprung-Russell diagram. So that's really exciting. Don't everyone all rush up at once and get all excited, please. The crowd goes mild. So we're going to talk about that shortly, but that's just, I find that so exciting. You can start to plot these babies, plot them on a graph. Okay, this is recapping just the diagram here that I had earlier on here. So here's your clump. It's a protostar still enshrouded with cloud, but you can see the disk forming and the jets forming. That provides a very important mechanism to allow more mass to accrete. Now you're getting into pre-main sequence stars, and notice the size is coming down here. You're getting down to 100 astronomical units, getting close to a solar system sort of size. So they're broken into class 2 and 3, and you can see here there's still a little bit of gas and dust, but nowhere near as much, and it's coming down onto the disk. The jets are still there to a degree, but not so bad. In class 3, you've lost your jets. And the disk, you can see little dots in that disk. It's now called a protoplanetary disk, and that's the little bit of debris that's left over in those disks, and they will become planets. And that's why your planets are always in the same disk plane. So that's just recapping then. So let's look at a little bit more detail here. So, yeah, your class 3, you've still got a little bit of gas and cloud around you here. Jets are still there, the accretion's still going on, but nowhere near as bad, and you've almost cleared all your gas and dust there. You can see it in the near infrared and a bit in visual as well. By definition, it's a pre-main sequence star. And then onto your class 3 with your protoplanets are starting to form. Time-wise, this stage here, your class 2, our sun probably took about 3 million years to get to there. And class 3, when you're starting to get what you call your protoplanets, just as you've got protostars and shrouded with gas and cloud, you get protoplanets. The beginnings of planets are forming from that disk that's left over because it's no longer accreting onto to the central core. This process to get our star to its inner temperature gets up to that magic figure of roughly 10 million degrees, whereby it can start fusing hydrogen to helium, and yay, it's on the main sequence. It's a main sequence star. Our sun, between 30 and 50 million years, and you might think, come on, slap, you know, sort your stuff out. You know, is it 30 or 50? That's quite a wager. You look up in the literature. Half it says about 30 and half it says about 50, so I've hedged my bets there. And I think it probably typifies that it's a whole field of astronomy that they're getting to grips with, and it's somewhere in there, and that will probably get narrowed down with time. And I'm sure it probably depends on the environment it's in and, well, a lot of factors going on there. All stars reach main sequence within 150 million years. Remember that concept that I told you, the larger things, because of more mass, more gravity, things happen quicker. So that's why in your handout there, for a 2 solar mass star, I think it said about 10 million years. Of course, the sun is only half that mass, so it's 30 to 50. And you're getting down to stars that are sort of, say, 10% or 20% the size of the sun. You're getting up to 150 million years. The smaller something is, the longer it takes, because there's less gravity driving it. Okay, now here's our Hertzsprung-Russell diagram. Once again, another little time talk about principles of astronomy. So there was 2 astronomers, Hertzsprung and Russell there, and they sort of discovered that if you had a plot, you got all these stars, and you measured their brightness and their temperature, which is really readily, it's a whole separate talk, which we will do, how to do that, and you plot them on a graph whereby you have the temperature in logarithmic fashion on the bottom. Ignore the funny figures here because that's 10 to the power, for example, 3.8, and which is about 6,000 degrees and so on. But if you have your surface temperature along the bottom, along the x-axis, cold down this end and hot down here, on your y-axis you put your luminosity, or essentially your brightness of your star, in a logarithmic fashion, and you get a cluster of stars and measure those 2 parameters and plot them. And it's lovely. You start getting stars start forming little groups. In the main sequence, these stars spend 90% of their life, where our sun is at the moment, in a stable state, burning hydrogen to helium. They're in a nice little diagonal going right up like that, right through up to 150, 200 solar masses. Here's our star here, 1 solar masses. So that's called the Hertzsprung-Russell diagram. It's a very important and useful tool in astronomy. Astronomers use. So they thought, well, why don't we start doing this for pre-main sequence stars? We can see them visually now. And what they've done here is they're able to do what we call evolutionary tracks. Okay, so let's just have a closer look at this here, see if I can get this little marker to work for me. No, it's having a little moment to itself, and that's fine. But you'll see the diagonal line. It might go, here it is here, this diagonal line at this end. That's the main sequence, and you can see in blue that's got written the mass of the star that ends up on that main sequence. Over here a little bit to the right-hand side, this doesn't want to go, then that's okay. I can relate to that some days. Oh, here we go, we're working now. This little line up through here is the start of the pre-main sequence star. The blue lines represent what we call evolutionary paths. In other words, how you follow a star, and it follows if you follow its blue line, and that tells you how with time its temperature and its brightness or luminosity, how it's changing with time. For example, let's go for a 1.5 solar mass star. You see it starts here at a certain brightness and luminosity. Just tee it up with the x-axis and the y-axis, and then so it starts going down this little track here. So it's losing its brightness, but it's roughly the same temperature. And something happens in the inside, which we'll talk about shortly, and suddenly it starts getting a bit brighter again, but also its temperature's rising, does a little loop here and so on. And you'll see for each mass, they do sort of slightly different evolutionary paths, so their temperatures and luminosities change with time. Now, the red lines are called isochrones, and they represent the time that has passed at each evolutionary stage. Just for example, let's go for our sun, shall we? Here it is here, 1 solar mass. And this isochrone here is 10 to the 7, which is what, 10 million years. So 10 million years would have passed to get to this phase here, and that will tell you how its surface temperature, and it'll tell you its brightness. So that's what an isochrone is. It just tells you the time that has passed at that evolutionary point in time. So this is a great graph. Why is it important? Because if you measure something, if you know its mass and you work out its temperature and you measure its luminosity or brightness, from there you can work out exactly where it is in its evolutionary path and what's going on with it. But also you can then test your astrophysical models, your computer models of what should be going on inside that star. Knowing its mass, you should know how it's evolving, and you should be able to work out, well, I predict it should be here on the graph. And all those models have been very, very successful in matching the observations. So here's just our figures again. The sun, to get to the main sequence, about 30 to 50 million years. 2 solar masses takes about 10 million years, and half a solar mass takes about 100 million years. So you can see that principle there. Okay, let's have fun. This is for some of you probably a little bit more technically minded. And these evolutionary paths, as you can see, they're broken into 2 groups. There's 2 obvious groups there. There's vertical paths, and there's horizontal sort of orientated paths. The vertical ones are named after a Japanese astronomer called Hassi Tracks, and the horizontal ones are called Henya Tracks. That's an American astronomer. So let's have a little bit closer look at these. It's worth doing. This is exciting sort of stuff. This gives you an illustration of how they can work out what goes on inside them. So the Hassi Tracks apply to all stars less than 2 solar masses. And here's 2 solar masses, so notice how they all have these verticals going on here, whereby a star starting off relatively bright to how it ends up on the main sequence, so it's relatively bright for its mass, but it starts getting dimmer and dimmer and dimmer, but its surface temperature remains the same. And when a star, or a pre-main sequence star rather, is on a Hassi track going down an evolutionary path, that tells you the whole star's just going through full convection. There's no radiation. Its interior is just churning over and over again. So you can see the smaller the mass, the longer it spends on a Hassi track. And that stays fully convective, usually until some Deuterium Fusion kicks in. That raises the heaters even more, and that's when you start getting some radiative zones kicking in, and you start getting the horizontal tracks. Now, I've got here a nice little slide for you, just recapping what's going on in the interior of these stars. So a pre-main sequence star, less than 5 solar masses, throughout its entire life as a pre-main sequence star, it's just the whole star is just convection the whole way through. Stars 0.5 up to 2, they have developed then a radiative zone later on at stage before they reach the main sequence. And here it is here, they have a radiative interior zone and a convection zone, and that's how they end up on the main sequence. And our star, of course, is a 1 solar mass, bang in the middle of that there. So that's what our interior of our sun looks like. Matches perfectly in with the models. It's got a core, then a radiative zone, then outer convection. And stars greater than about 2 solar masses, they have their convection zone in the middle because they're so hot, that drives, the heat gradient drives convection. And for the technically minded, you wonder why the radiation in the outer. It's because you no longer have such a high temperature gradient, but it's hot enough where it's ionized your hydrogen even in the outer layers. So ultraviolet light can quite happily zip through. It's not been absorbed. So that's what's going on there. So that's the Hassi Tracks. I don't mean to blind your newbies, just have a listen to this, but for the more technically minded. How about the Henya Tracks? These are the horizontal ones, and you can see here where the temperature of the star is starting to rise. the surface temperature, and starting to get a little bit, luminosity increases a little bit too, and it does a little bit of a loop there. So increasing temperature with a steady luminosity. And this is, as I've alluded to, this is when the star has developed a radiative zone, either inner radiative or an outer radiative zone. And it's all stars greater than 5 solar mass, 0.5 solar masses rather, have to do eventually develop a radiative zone, as you can see here. And 2 solar mass pre-main sequence stars, by the time they've reached the stage, or by the time they've become a pre-main sequence star, they're already big and hot enough, they're actually up and running with radiative zones. So they don't mess around with the Hassi track, they leave that to the little boys. They move straight onto the Henya Tracks, yeah. So I just throw that in there, a little bit of extra depth, and people ask questions about what's going on. So there's 2 types of pre-main sequence stars, and you can see the relevance of all this now. The T Tauri stars are less than 2 solar masses, which tells you that at some stage they're fully convective. Herbig A and B stars are 2 solar masses up to about 8 solar masses, so above 2, which means they're the really big hot ones. They're always radiative zones going on in their interiors. So let's have a look at these T Tauri stars. You can see them here, and pretty much we've really spoken about this, but just recapping. 0.5 solar masses, they're fully convective all of their life on the pre-main sequence, and those going up to 2 start off convective and then go to their develop radiative zones, which we've talked about. So how do you identify a T Tauri star when you're looking at it? This is actually the very first one that was identified, the protostar, but there's criteria. And as I alluded to before, stars are classified by their spectra, and that's where you put a spectroscope in your telescope that splits light up. Subject of a whole talk, but you can tell a star's temperature, its composition from there, and so on. So stars, the big hot stars on the main sequence are O's, and they go down in size and temperature to B, A, F, G, K, and M. Once again, you think, jeepers, guys, whatever happened to A, B, C, D alphabet when I went to school? And once again, historical reasons, they classified them A, B, C, D according to hydrogen emissions and so on, and they realised, oh, actually that wasn't a clever idea, but we'll keep the numbers the same. So that's the only reason there. So stars are classified by their what they call their spectral classes and their temperature, and where. Now, so T Tauri stars are by their location. They've got to be near a region of star formation, near a molecular cloud or a nebula, and their spectra, their temperature. They're very variable, very feisty. They're often known as the feisty adolescents of the galaxy, these T Tauri stars, and how bright they are. Because remember, they're the lower ones, so they're very bright, high luminosity for their masses. And sure enough, here's their criteria here. So they have to be highly luminous, classes F, G, K, and M spectral classes, which refers to meaning the surface temperature is somewhere between 2,000 and 8,000 degrees. And they have to be near some molecular clouds. And typically they have to be very variable, highly variable in brightness, the luminosity. And that's, as my little GIF image there sort of illustrates there, that's typical of T Tauri stars, and that is actually one of their criteria. Now, why are they sort of so feisty like that? They have variations, large variations in brightness on a regular basis, but also on a non-regular erratic basis. The regular basis on purpose and function of days is because, remember, these things are pretty volatile, they're fully convective, so there's a lot of activity going on their surfaces, so they have very bold, large sunspots on them of intense magnetic activity. And as this protostar rotates every few days, you see that same sunspots come round, and the sunspots are large enough whereby they actually dim the star down. They have random variations anywhere from minutes to years. Because instability in the disk, you've still got material from the disk accreting onto the surface of the protostar, and as I mentioned before, it's not perfect. You get infalling clumps, so you get these bullets coming out of the jets that light up and ionize the area around them as well, and that also causes variation. And you get a lot of surface solar flares going on. They're pretty volatile sort of surfaces, so they're very, very volatile, and that's one of the reasons. The variability is one of the criteria. Okay, so let's have a look at some. That was the first prototype in the constellation Tauri. It's a 3-star system. They're all T-Tauri stars, less than 10 million years old. And here's a reflection nebula here. It's not so obvious, but that's a reflection nebula. You can't see it so well here, but if you look close up, you can see the jets out here, and there's little clumps out here, 3 Herbig-Haro objects with large jets. So that, and of course, if you did your temperature on that, would somewhere between 2,000 and 8,000 degrees, and you know, that's a T-Tauri star. So that's those. How about the bigger stars between 2 and 8 solar masses, the big Herbig A and B? So as you saw in that original diagram, I showed the spectral classes. The A and the B are big hot ones, just short of being O class. The E stand for emission. So when you have your spectra, you look at a main sequence star, sort of goes up like that, like a bit of a hump, and comes down with the brightness of the wavelengths of light. And you see big dropouts, what they call absorption lines, where there's atoms in the atmosphere of that main sequence star, and it's absorbing the light as it leaves the star, so you get little dips. These Herbig stars are pretty angry stars as well, so they have emission lines where actually there's really energized, ionized elements, in particular calcium and hydrogen in the atmosphere, that are giving their own emission lines. So their spectra really is something different to your normal main sequence stars. They spend all of their time on that horizontal Henya track. That's so 2 solar masses. So in other words, by the time they have finished their protostar and onto pre-main sequence stage, they are up and blazing away with radiative zones. Higher mass, higher temperatures develop radiative zones. So how do you identify them? What are the criteria for Herbig stars? Once again, location and spectra. So here they are. Here's your big A and B stars, a heck of a lot brighter, whereby their surface temperature is anything up to 8,000 to 20,000 degrees, so much hotter than your M, K, G and F stars. They are near reflection nebula. So reflection nebula, I never mentioned those earlier on. So we mentioned those H2 regions, those emission nebula, because the big massive stars blasting at ultraviolet light, exciting the hydrogen, causing it to glow. The big massive stars then all go supernova, blow up, leave the scene, and then you get in your more average sort of stars are coming up, and they're shining out more lower energy light and visual wavelengths, and the visual wavelengths hits a lot of the dust and just reflects off it. And what does light look like when it reflects off dust? Look upwards in the middle of the day, blue. So you get these blue reflection nebula, they're called. So the near reflection nebula, spectral type A or B, you know, with your temperature up to about 20,000 degrees. And as I mentioned earlier on, they have really strong hydrogen alpha and these calcium H and K emission lines. Those are all emission lines in visual wavelengths. Okay, and here it is here. Here's an image of one such Herbig object, of a Herbig star. Here's your blue reflection nebula going on, and if you looked at that under your spectroscope, you'd see these prominent calcium H and K lines. So that's summary, that's of the objects of star formation. That was a lot of information to take on. Let's just bring it together to a nice flow diagram. So you start with your giant molecular cloud, down to your protostars that still got the gas, these T-Tauri and Herbig, and then onto your main sequence. So here it is here. These giant molecular clouds, light years across, they're supported by those magnetic lines embedded in there by the gas temperature. They then start, there's various things that can trigger them. They start collapsing and fragmenting and cascading into smaller and smaller fragments. They then develop a dense core, which by definition is a protostar. The protostar, by definition, is enshrouded in dust, and it's in a state of hydrostatic equilibrium. You're getting further gravitational collapse. You're getting some deuterium fusion, particularly in the bigger stars. That's ramping up the heat more, so allowing more mass to fall onto them, puts them on the Hassi Track with their radiation zones, and you're getting disks and jets forming in that area in that time. The pre-main sequence stars, by definition, has cleared most of the dust. Then they split up to your T-Tauri stars, less than 2 solar masses, highly luminous and variable. And then you've got your Herbig stars over here, A and B stars, which are a lot hotter, and they have those prominent emission lines in their spectrum. Eventually, the relevant cores get hot enough, up to 10 million degrees, and they're hot enough to start fusing these protons of hydrogen together to form helium for party balloons. and you could, by definition, you now have a mature star on the main sequence. As I've mentioned here, of the ages, how long does it take, the range? Some of those really massive stars can be up and running in about 3 million years, so the range is from 3 to 150 million years, and our sun somewhere between 30 and 50 million years to develop from woe to go. I put this here, this is just a good visual if we're thinking about our sun, so you've got a clear idea in your mind, how did our sun form? So it would have started off this giant molecular cloud, it would have formed into a protostar, and sort of this whole period would have, protostar period, class 0 and 1 would have taken about 300,000 years, gone through into a pre-main sequence stage that would have lasted somewhere between 30 and 50 million years before it became a mature main sequence star, which it is in the sky today. I've just got some images here, and this is just some of the Hubble telescope is primarily visual wavelengths, but it does dip a little bit into the near infrared, and I just wanted to highlight. Look, here's 2 Hubble images. This is invisible wavelengths off that Eagle Nebula, M16. Look at these big dark pillars. The only reason you can see them is because of the dust is just sort of blocking the light from shining. Look, you're dipping a little bit to near infrared. Check that out. Suddenly you can see all the light shining through the dust. Isn't it crazy? So that's the power of infrared telescopes. Here's the James Webb. We have now seeing through the dust, you're seeing the light come through of these hundreds and hundreds of infant stars shining through here, but also you're actually seeing the dust itself. See this little lava-coloured red dot here? Little patch here, little patch up here, little patch here, big patch here. They are all bipolar jets and Herbig-Haro objects going on there. And then I just showed here, you start going from the near infrared to the mid infrared, and you're actually getting a better picture of the dust. You've lost all your stars now, but just I'll put this in here just to illustrate, if you go further into infrared, they're going to actually tell more information about these regions. So even get a better idea of what's going on in these giant molecular clouds even before they form protostars. So that's very exciting. Okay, so to conclude, so tonight you have learnt where stars form, how stars form and develop, such that you can look at images like this and this, and be able to identify infant stars in their various stages. And importantly, sound effects, tomorrow you'll be able to point up to the sun and tell someone exactly, with the use of your handout as a tool, how the sun formed and matured into the star it is today. I hope you've enjoyed revealing the youngest stars in the galaxy. Thank you. Any questions? Yes, Robert.
Where would our sun be on that Hertzsprung-Russell?
Yeah, sure, the Hertzsprung-Russell diagram. Oh, okay, that was all pre-main sequence. We're main sequence now, so we're sitting on the main sequence.
Right, so you don't change after the main sequence, right?
There's a little bit, the main sequence is not, strictly speaking, not a sharp line. It's got a bit of width to it. But relatively speaking, it's a sort of relatively straight line, instead of those big evolutionary tracks onto red giants and stuff. But if you just want to focus in and blow up on the main sequence, there's a bit of width to it. And our sun is increasing its luminosity very slightly. Well, slightly in terms of the big picture, but we are getting hotter because of the luminosity, not climate change today, but you know what I mean, and over thousands of years, tens of thousands, millions of years, the sun is getting slightly more luminous. And that is because as we're burning more hydrogen into helium, the helium's sinking down, and that's just raising the temperature in the core, the pressure and temperatures in the core, so its luminosity within the main sequence does go up. But relevant to Earth in the long term, over hundreds of thousands, tens of thousands, 100,000, millions of years, but not on the little time frames that you and I need to worry about. But it does. So, and answer your question, there is a bit of wriggle room on the main sequence. It's not totally a straight line. Does that sort of answer the question? Yeah. Yeah, but we're on the main sequence on there, yeah. Yes?
What keeps such a big cloud of dust together? Why doesn't it just drift apart?
So why doesn't it drift apart? What holds it together? You've got two forces. It's gravity holding it together. So in answer to your question, why doesn't it fly apart? Gravity. And what's stopping it from completely collapsing in, of course, is the bit of gas pressure going on and the magnetic field lines controlling the particles to a degree, charged particles. So that keeps it together, and that's in perfect balance with the gravity pulling in. It's a constant between the two, in the state of equilibrium. So it answers your question, it's gravity that stopped it from just flying apart. Because remember, those areas in all of space is not full of molecular clouds for that reason. You know, you just get these large, dense molecular cloud, and they're high density, so you've got more gravity. Remember the density, you've got 100 to 1,000 times more particles per cubic centimetre than, say, the space around the sun, for example. So there are extra dense regions, there are extra cold regions, so they're packed in there, and that's enough to keep gravity to hold them together. So in answer to your question, it's gravity that stops them falling apart. Yes?
Does it ever go wrong? So as stars are forming, something interrupts that?
Good question. So the question is, do things ever go wrong? You know, this is the model process, how things go in an ideal world. We don't live in an ideal world or an ideal universe. I'm sure crazy things, you know, stars getting underway, you think, oh, I'm going to be a protostar any day now, marking off the days on the calendar, and then suddenly some massive star decides, I'm going to put an end to your plans, mate, I'm going to go supernova and blast you to smithereens. So I'm sure a lot of that region, it's a pretty crowded region, you know, those regions, so I'm sure things go astray and things go amiss and mishaps happen and things stray off the beaten path. That's the model. Yeah. So good question. Yeah. I'm sure it's a pretty busy place and all sorts of crazy things happen. Yeah. Yes.
If you're out there in a spacecraft,
yes,
in the vicinity of a bipolar flow,
yes,
jet, and you'd be bombarded with charged particles,
yes,
how would you experience that?
I think, to be honest, so the question is, say, for example, hypothetically, you're in a spaceship, and you're travelling through space and you hit one of these regions of jet outflows. So, to start as I'm sure the jets aren't totally, you're talking huge distances, light years outward, so, and that you saw them fanning out as well to a degree. So I'm certain you wouldn't be necessarily in an area where 1 minute you're in a jet and you're out of a jet, and it would be a gradual thing you'd be experiencing because we travel relatively slowly. But hypothetically, I would have thought you'd be bombarded. You know, it's already ramming into interstellar medium, creating these massive shock waves, you know, enough to ionize material. In the spectrum there, you're not talking just hydrogen and stuff, you're talking all sorts of elements are getting ionized. So I would have thought it'd be pretty hostile to life and hostile to any contraption that we built, I would have thought. Yeah, because it's pretty concentrated as well. It's pretty hot, high velocity. Yeah, so I would have thought you wouldn't be, you know, it would be pretty, very, very hostile as in terms of, yeah, I don't think you'd survive it, I wouldn't have thought. But yeah, good, you think about things like that, didn't it? Yeah, because you could argue, well, how dense is it in terms of how sparse it is, but you still got pretty high-powered charged particles and powerful radiation going on, and I think that would be your demise. Yeah, but good question. Yeah, Andrew.
Yeah, these giant molecular clouds must date from the Big Bang, and they've just been sitting there ever since, but most of them would have been consumed in star formation. So I wonder what percentage are left from the original molecular clouds.
Yeah, so after the Big Bang, sort of it's dark matter that grouped all the baryonic matter together. So Andrew's saying what's, you know, if all the original gas and dust from after the universe first formed, how much of it's probably converted to stars now, how much is left still to go, is the question. And interesting, similar to your question that you asked Niven, I think, 2 or 3 months ago. You know, when is all the gas, is it going to run out one day? And the answer is yes, it is. Of course, you know, new generations of stars go supernova and enrich the next lot and will create more gas and dust, and that's how you get generations of stars. And of course, your stars up to 8 solar masses develop these planetary nebula that puff out in their layers and so on, enrich. So you've got all that processes going on. So there's a lot of recycling. But yes, eventually it will run out in terms of, I think I said to Niven a few months back, I said, because you just look at these elliptical galaxies, star formation-wise, they're dead. There's no star, there's no gas. The gas and dust in those big, massive elliptical galaxies out there are dead. There's no gas and dust left. It's run out. and you only tend to get star formation predominantly in these spiral galaxies, or you get two galaxies colliding, the starburst galaxies. But essentially, you tend to, the lion's share of it's only in these spiral arms of these, where you get all the gas and dust that's settled in once again to a nice disk, the formation of the galaxies. And the spiral arms are just actually spiral density waves that plough through them to bring them together. Some recycling. But yes, now what sort of time frame? I would imagine you're talking billions of years. But yes, galaxies run out of gas and dust. Look at elliptical galaxies, they're dead. Yeah. Oh yes, there's a question on the back, sorry.
What is dust made of? Is it carbon or silicon or anything?
Yeah, what is dust made of? So, yeah, cheers, mate. Yeah, a lot of carbon, silicon, carbon, magnesium. Of course, carbon, yes, why? Because it's the third most common element in the, hydrogen, helium, oxygen, carbon, fourth most common element. So oxygen, carbon, silicon, magnesium, and so on, all the things that go to make up typically your soot, your hydrocarbons, full of what they call it polycyclic aromatic hydrocarbons, which are big circular chains of hydrogen and carbon, which essentially is soot and stuff. Yeah, all the ingredients. They've even found water, with their spectroscopy and stuff, these high-resolution spectroscopies. They've all sorts of organic chemicals, but water they've found in these, so they're quite rich in these giant molecular clouds that go to make up that dust. Dust serves a very important, obviously if it wasn't for dust, wouldn't be us. Dust is a byproduct of previous generations of stars. The first generations were just hydrogen and helium. They fused it all together to make the heavy elements to distribute it as dust. So, but the dust also serves a function for star formation in that it radiates the heat away. The stars blaze up energy and the dust absorbs it and re-emits it in infrared, so it helps to radiate heat away from the gas cloud, so which is more likely to start collapsing down onto your gas cloud. That's another factor that promotes it to collapse down. So yeah, and that's why they say we are made of stardust. Yeah, it's almost anything. It's very rich. Stardust is very rich, but predominantly your silicons, carbon, hydrocarbons, and so on, organic chemicals.
So, building on that there, I thought that when the Big Bang first happened, all these extra elements that made up all those dust was not there.
Correct.
So it had to have stars form and
Yes.
then explode to create dust.
Yes.
So perhaps we're going to get more dust from stars.
Oh yeah. So the first generation of stars was just hydrogen and helium, because that's all there was after the Big Bang, a little bit of lithium in there. But essentially, for practical purposes, just hydrogen and helium. And the first stars were just hydrogen and helium, and all those elements, your oxygen, your carbon, your silicon, and all down the line, all of those were forged inside those first and second generations of stars. Were all forged in the cores of stars. When you, as I mentioned on the main sequence, stars spend 90% of their life on the main sequence burning hydrogen to helium. And that's 90% of their lives. They, like all good things run out, and they run out of hydrogen. They've fused it all into helium. But the temperature slowly rises up to a certain point, to about 100 million degrees, and then helium fusion kicks on, and helium creates carbon and oxygen. And then the temperature goes up again, and they start fusing heavier elements, and eventually the star will, if it's up to 8 solar masses, will puff out its outer layers. You know when you see those lovely big pictures, like pictures of eyes and stuff in the sky, those lovely big fluffy pictures, all different colours. They're planetary nebula, they're just dust all spreading out. And then you've got your supernovas and your big stars, more than 8 solar masses, that just go boof. And the reason they go boof is because they get right up to iron, fusing heavier and heavier elements into iron. Iron, when you start fusing iron, instead of generating energy, it absorbs energy, so the whole star just collapses onto itself and then rebounds. And in the huge shock waves that through all the material of the star, more elements get rammed together, neutrons get added on and stuff, and then they decay to protons, and you get heavier and heavier elements. So most of all the heavy elements are forged inside stars. So it's only your second and third generation of stars now that we're getting, that makes up us planets. So in other words, there would have been no planets around the first generation of stars, because it was only hydrogen and helium, no dust. So dust, you're quite right. So I think Robert's comment was there was no dust in that first generation of stars after the Big Bang. It was all hydrogen and helium. Does that sort of answer where you're coming from?
Yes.
Yeah.
So is that how we acquired on Earth the deposits of living heavy metals like uranium, for instance.
Yep, supernova explosions and the like. Yeah, yeah. In fact, one of the reasons they know that a supernova explosion happened in the vicinity of the sun when it was the process of forming, because they look at the isotopes of aluminium, and I think it's aluminium-26, I think it is one of the isotopes of aluminium is only formed in supernova, and it decays after about 26,000 years, its half-life. So the fact that it's locked in to our meteorites and stuff, they can see locked in aluminium-26 isotope, they know that that came from a supernova in the vicinity within the 26,000 years, which, look at those figures there of star formation, that 26,000 years is nothing. So all what makes us up is from all the heavy elements in particular. Now then you've got neutron star collisions called kilonovas. So you get your supernovas, but you get kilonovas, and that's when you get two neutron stars colliding, and that creates a big explosion, and that creates a lot of our gold and silver and palladium and so on. Have a look on the Google periodic table of elements according to source or something like that now. And they've got the periodic table of elements, but they're all colour-coded, where each element came from, whether it's from small mass stars, supernova explosions, or neutron stars combining. So it tells you all that stuff. But most of the heavy metals, those heavy elements, are from massive supernova explosions or neutron stars colliding. And your carbon and oxygen, silicon, all that sort of stuff that's really, 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 really abundant, relatively so, is all from forged inside stars through nuclear fusion at their cores. Yep. Still to this day, 98% of the universe is hydrogen and helium. Yeah, and only all that dust stuff is only 2% by mass. And then you've got oxygen is the most common one, carbon, and so on. And what's the most common molecule? People say, will aliens be carbon? Of course they will, because it's the most, you've got hydrogen, helium, you've got carbon here, and silicon and stuff way down there. The commonest things occur commonly, so it's going to be oxygen and carbon compounds. Yep. And that's why water is so abundant. Hydrogen is the most common element in the universe. And you've got helium, that's pretty inert. It's the only use for that's for party balloons. And then you've got oxygen straight underneath it, and H2O. That's why water is so vital and so wonderful for life. Yeah.
It will be the same in other places.
Yeah,
In the universe too.
exactly. And that's why there's the expression aliens drink water, because they will. The commonest things will be across the... It's not if people think, oh, we're so special. We're made up of the commonest elements in the universe. If we were made up of some rare isotope of boron, I'd say we might be special, but we're made up of carbon and oxygen and hydrogen and stuff. We're made up, and the aliens out there, they'll be made up of the same stuff. Stardust, yeah. As was who was the guy, Carl Sagan said we're made up of stardust, yeah.
From going back to the formation of
Yes.
the protostars to main sequence,
Yes.
what part in that sequence fails to create brown dwarfs?
Yes, so essentially, you're saying, I was talking about how a star gets to a main sequence. The question is sort of alluding to, where do you go for a brown dwarf? A brown dwarf is a failed star that has not been able to reach the main sequence. It's just not big enough to have enough mass to create the high enough temperatures to get up to that magic 10 million degrees to fuse hydrogen. And those are stars, your main sequence stars, as you went down the line there, your red dwarfs are the lower ones, and they go down to about 8%, 0.08 of a solar mass. And anything below that it's just not enough mass to create the temperatures to get nuclear fusion and become a red dwarf. So they're called brown dwarfs, failed stars. And you then drop the whole thing of solar masses, and you go to Jupiter masses. So the mass of Jupiter, instead of a big M with a picture of a sun and a dot, you'll have a big M with a capital J as a subscript, meaning Jupiter masses. And brown dwarfs typically are between 13 and 80 Jupiter masses. They are big enough to burn deuterium in their cores. Some of them even burn a little bit of lithium in them as well, but they just don't burn hydrogen. So in answer to your question, so they are out there. They're just brown dwarfs, and they're just not stars. They're failed stars, because a star by definition is fusing hydrogen at its core on the main sequence. So they're called failed stars. They are out there, and they take ages to form, but they are out there, yeah. Does that sort of answer your question? Or is it something you're wanting to know, something a little bit different about brown dwarfs?
I was wondering, where in that process? Like you have protoplanets, you go along, removes the dust clouds, do all the jet stuff, becomes
Yep.
the main sequence.
They would all do that all to some sort of degree. Now, whether or not, and I suppose you're getting me thinking now, because that's a good question, is at what stage is there not enough mass? That little clump is so small, there's not a lot going on in there to generate disks and jets. And is that sort of probably the angle you may be going at? That's a good question. I don't know the answer to that. I might actually have, out of interest, I might have a look into that. At what stage do you no longer have those jets and so on? I don't know, but yeah. But the bottom line is the end result is a brown dwarf. It's just not big enough. But yeah, there probably is a certain threshold out there below which certain mass, you just don't get your disks and your gas. I don't know, is anyone else sort of... because that's an interesting question. At what point is the threshold you no longer see jets and disks? But once again, everything in life, life is not black and white. Life's very fuzzy. And, a little bit of this and a little bit of that. And I suspect you might just, if you look hard enough, a bit of a jet, bit of a disk may be going on there. Slight one, it's all a gradient, I suspect. But yeah, good question.
A brown dwarf could be stripped of the gas around it, possibly by a brighter star igniting nearby.
Yep.
And it clears its area.
Yeah. And also, it's the jet and the disk, that function that allows a protostar to get more mass too. And as I said, those early protostars only have 1% of the mass of their final mass on the main sequence. So if a star is small enough and it hasn't got, let's use the word substantial or significant jets, it might have a bit of a pathetic excuse for a disk and a jet, if you know what I mean, bit of a wussy jet. And disk, the pathetic excuse for one maybe. A little bit forming, because that's a natural, a disk will want to form. There must be enough cloud for it to come down to form an object, albeit a brown dwarf. And we know it's a law of physics that if you get something spinning around and coming down, particles will start colliding and they will form a disk. You will have a degree of magnetic fields going on with bipolar jets, but they're not going to be very big or very strong, yeah. And at what stage is just nothing going on there. And I suspect that's where you're getting into sort of planets and sort of exoplanet material, sort of, which is anything below about 13 Jupiter masses.
Got one from the internet, Chris.
Oh yeah, forgot about the internet. Hi guys.
This is from Jason. He says, silly question, sorry. Does the percentage of hydrogen in the dust determine the type of star formed, i.e. garbage dust equals dim star, or lengthen the formulation time, or would the heavier dust get thrown off?
So what was the last two aspects of that question for Jason?
Is it the amount of hydrogen, percentage of hydrogen in it? Like
Yep.
if you'd have dust which doesn't have so much hydrogen, do you get a dim star? I
Right.
think he's saying.
Yeah. Okay, good question. Was it Jason? Yeah, Jason, good question. Turning it around a little bit, astronomers talk about metallicity. And it's because hydrogen is so predominant, it's the predominant by far by country mile. Of all the materials. So it's easier rather than look at hydrogen percentages to turn it up on its look at what they call metallicity. And for you and I, metal is something hard and shiny and stuff, or something you walk on the road. But astronomers are funny. Anything metal is greater than hydrogen and helium, atomic-wise, like oxygen, carbon, and so on. They're all metals. And astronomers talk in the term metallicity, percentage, not so much the percentage of hydrogen, but the percentage that's not hydrogen or helium. And for example, our sun's about 2% and so on. And metallicity does affect the development of star formation, how much mass. It's a whole field of astronomy that all the fine details are sort of over my head. But I do know that the early stars that had zero metallicity, that were all hydrogen and helium, were so big, they just were able to get very, 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 very large, that metallicity seems to put a constraint on how big you can get. So in terms of how dim, now, yes, you can get stars that get more dust around them during the state of their evolution. That makes them more dimmer and change in variability. And a classical example is Betelgeuse. It's a red supergiant. And everyone, about 2 or 3 years ago, everyone's going, oh my God, have you heard Betelgeuse is going to blow at any moment because it's changing its variability. And they soon worked it out. It was actually just a lot of dust, a big cloud of dust moving across it because it's produced a lot of dust. So dust does affect it. Your T Tauri stars, look how variable they were. And that's because of clumps hitting them, And I'm sure a lot of that, there's dustiness still going on around them. But admittedly, they were all pre-main sequence stars, but early in that pre-main sequence stage, there still is a little bit of dust. That would affect it, yes. In your protostar phase, of course, by definition, it's completely enshrouded in dust, no matter what composition it is. So if you do have more dust in a star, it does make it appear dimmer. Hope that answered your question, Jason. Any others? Otherwise, you guys online, everyone here got a treat. I can't give you a treat online, but they also got a handout, and feel free to send me an email, membership@astronomy.org.nz, if you want a copy of the PDF handout. It's about 5 pages or something like that, just talks about and gives all the graphs and stuff that we had here today. Otherwise, I think, is it good night time, Steve? Yeah. See everyone online, and thank you everyone very much for a lovely evening. Thank you.